In this video, we will learn about how to apply Biot Savarts Law to measure the magnetic field of a circular loop as a function of current and as a function of loop radius and distance from the loop. Suppose a current carrying wire carrying a current I, and the magnetic then according to Biot Savarts law, the magnetic field experienced at a point O will be equal to mu naught upon 4 pi, which is constant, and I, the current carrying from through the wire, the small element dl, this, and sine of theta. The theta is the angle made by the current element dl and the line joining the point and the element, and is inversely proportional to r square, where r is the distance between the current element and the point. Suppose a circular current carrying conductor carrying a current I. So at a point at a distance x from the center of the coil, the magnetic field Bx induced will be equal to mu naught Ni upon 2, where n is the number of loops, and r square, r is the radius of the circular loop, divided by x square plus r square whole raised to power 3 by 2. And according to tangent law, when a bar is suspended in two perpendicular magnetic field, it will come to rest, make an angle theta, which is theta with the BH, horizontal component of the earth. Suppose this is the horizontal component of Earth's magnetic field, and Bx is our magnetic field, external magnetic field. So the magnetic needle rests at an angle theta with BH, and then magnetic field will be given by B equal to BH tangent theta, and this is known as tangent law of magnetism. In this experiment, BH is equal to horizontal component of Earth's magnetic field, and theta will be the deflection in the needle because of the two fields, the one because of Earth's magnetic field and other due to current carrying coil. And we assume BH is equal to 3.5 into 10 raised to power minus 5 Tesla, and then magnetic field, total magnetic field will be given by Bx equal to BH tangent theta. Let's start with the experiment. These are the apparatus used: ammeter, battery, key, rheostat, commutator, and this is the circular loop, and this is the compass box. So commutator is used for changing the direction in the coil while the direction in the rest of the circuit remains in the forward direction. So first do the initial adjustment, like make the axis of the current carrying coil at 90-90, joining with the 90-90 line of the compass. Now the line joining 90-90 is parallel to the axis of the coil. Second step is now rotate the whole apparatus so that this magnetic needle lies along the at zero deflection. Now now magnetic field is at zero. The deflection in the compass is zero. Show normal view. Now make the connections according to this circuit diagram. The emitter is connected to battery, and then battery took the keys and one end of the key to the rheostat, and rheostat to commutator, and two keys are connected to the circular loop. And one end to the battery, one end of the commutator to the battery. Now the circuit is completed. Insert key. Now we'll see that current showing in the emitter is 1 ampere, and when we zoom the compass, we'll see the needle which initially lies along to 0 degree, now deflected to 75 degrees to both angle. Okay. As we reverse the current by this knob, again it's lying on the 75 to 76. So note down theta 1 and theta 2 for both cases. We can also set the number of turns of the coil from 10 to 45 and set it any one of the, say, set it for 20 turns, and we can also change the radius of the coil from 5 to 10 centimeter. In the normal view, and we can also change the current by adjusting the rheostat. As we change, we'll see as we adjust with the rheostat, this current, the value of current changes. So take different values of current and note down the deflection of the needle. Now it's 81 to 80 to 81, 80 and 81, and reverse also 81, 81, and as we change the current, the deflection changes. Okay. This is the table for different value of current written here, and note down theta 1 and theta 2 for the direct and reverse current. Take mean of all the angles and then find tangent theta, and then we'll obtain the magnetic field at the for that particular current, for that particular value of current. And we can also compare it with the magnetic field as calculated from Biot's law given in the previous equation. Similarly, this is the first part of the experiment. Similarly, we can calculate for the radius of the loop. We can also change the radius of the loop. We see there is a very negligible change. And note down the all values of the radius and corresponding deflection of the needle. Now the third and last part of the experiment. Now set it I'll say 6 centimeter radius of coil, and now don't change these values. Now the third and adjust the rheostat to max minimum. Now the last step is just to change this position of the compass with the center on both sides. Suppose on the right side at 5 centimeter. Zoom. Note down theta 1 and theta 2, and for reverse current also. Then again change this value to some other distance, and again note down these value, the theta 1 and theta 2 for both forward and reverse current, and so on right hand side and also on the left hand side also. And note down the deflection, and in this table we will calculate the distance from the center, that is x, and when the direction of the compass on the left side, note down theta 1 and theta 2. When the direction of the compass box on the right side, note down theta 1 and theta 2 for direct and reverse current. Take the mean of all the value of theta, and we'll calculate the Bx from the tangent law and also from the Biot Savarts law, and compare these two values. The x, the position of the compass along the axis of the coil, and versus the magnetic field induced. That's all for the experiment.